Hi guys, it's Daniel here, and today we're going to talk about the reflective properties of conic sections. It's a pretty interesting property of conic sections that isn't talked about very much, and it can generate a lot of unique challenging problems. Not to mention that it also has some practical applications. So without further ado, let's check them out. So first on the list here we have a parabola. If we shoot a vertical ray down onto the parabola and it reflects off, then the reflective property of parabolas says that this reflected ray will always hit the focus of the parabola. So as we can see here, no matter where I move the point, the angle of incidence is equal to the angle of reflection, which basically shows that this is indeed true. As you can see, it's pretty cool. And if you think about it, if we have a light source at the focus, and then we shine a light in a sort of like parabolic mirror, then all the light rays will all shine exactly vertically, and this is a pretty useful way to direct all the light rays in one direction. So let's look at the next one. This time it's an ellipse. So what the property here says is that if we shine a ray from one focus and then it hits the ellipse and then reflects off, it will always go to the other focus, no matter where we shine the ray at. As you can see, the angle of incidence is still equal to the angle of reflection. And this is a pretty interesting idea because, for example, if you create a pool table that's shaped like an ellipse, and if you place a billiard ball on one focus and you hit it anywhere, it will always pass through that one point on the opposite side. So that's pretty interesting. And finally, we have the less well-known property of hyperbolas. So this property states that if we shine a ray from one focus onto the normal line at a point of the hyperbola and it reflects, then it will hit the other focus. And as we can see here, the angle of incidence is still equal to the angle of reflection, so this is clearly also a valid property. And this is the least well known of them. You might have known the first two, but you probably didn't know this property. It's pretty cool. So, now that we have some knowledge on these different properties of reflection of conic sections, let's try an application on a math problem. So, what this problem says is let the focus of the parabola y equals x squared. Let's draw that here. Y equals x squared. Something like that. Be f1. Okay, so the focus here is f1. And let the point on the line y equals 1. So that'd be around here. Y equals 1. Be f2. So let's just draw a point here, f2. Now suppose an ellipse has its foci at f1 and f2 and is tangent to the parabola. So this is going to be the hardest to draw, but hopefully I can pull this off. Something like that. We have an ellipse that is tangent to the parabola. If the tangency point has the same y value as f1, so these two are the same y value, then we have to find the distance f1, f2. So if you didn't know the properties of reflection of the conic sections, this might seem like a very hard problem with a bunch of calculus bashing and a bunch of random variables that you need to solve, and it's just a headache. But let's see what happens if we use these new properties that we learned. Well, first we see we have a parabola and an ellipse that are both tangent to one point. So let's draw the tangency line right there. something like that. And now, let's see what happens when we shine a ray from F1 onto the tangency point. Well, if we do that, then it goes from here, and note that the property of reflections for the parabola says that this will go perfectly vertical. So if we reflect it, then it will go perfectly vertical like that. And now let's look at the ellipse. The property of reflections for the ellipse says that if we shine a ray from one focus, it should always pass through the other focus. And indeed, we see here that I've made it so it passes through F2. Now, what does that tell us? Well, that tells us that if this tangency point is t, then t and F2 share the same x value. So now we also know that t and F1 share the same y value. And since the y value of F1 is just 1/4, this is just a direct calculation of the focus point of y equals x squared. So this is 0,14. So therefore, this t is in fact has a y value of 1/4. And since it's on the parabola y equals x squared, it has an x value of the square root of 1/4, which is 1/2. So this point is in fact 1/2, 1/4. And finally, as I was saying, this x value of t is the same as the x value of F2. So therefore, the coordinates of F2 must be 1/2 and 1, because it lies on the line y equals 1. So now we're basically done with our problem, because we want to find the distance F1 to F2, and we know the coordinates of F1 and F2. So we can just apply the distance formula to get that the total distance d is equal to the square root of 1/4 minus 1 squared plus 0 minus 1/2 squared, which is equal to 9/16 plus 1/4, which is 4/16. So this entire thing is equal to the square root of 13 over 16, which is equal to the square root of 13 over 4, and we are done.
Hey guys, I'm back with another math video. Today we're going to be doing a folding problem from HME 1991, problem 29, and right now, pause the video if you need to.